For years, astronomers knew something was missing. Not dark matter, but ordinary matter, the same kind that makes stars, planets, and life itself. A huge fraction of it seems to vanish into deep space. Then, from billions of light-years away, strange millisecond flashes called fast radio bursts begin crossing the universe, and they carry the answer with them. Tonight, this video explores how these brief cosmic signals help reveal the hidden matter between galaxies. If this kind of deep space mystery fascinates, please like the video and subscribe for more calm journeys through the universe. At the widest scale, the universe presents itself as a ledger of contents rather than a simple field of stars. Light marks some of what is there, gravity reveals more, and decades of measurement show that the shining part is only a thin layer laid over a much larger whole. In this broad accounting, most of the cosmos is not made of the familiar material that forms stars, planets, gas clouds, oceans, rock, and bodies. Most of it belongs to darker components that do not behave like ordinary atomic matter. One part is dark matter, which exerts gravity yet does not glow in the usual ways. Another part is dark energy, a name given to the large-scale effect associated with the accelerating expansion of the universe. Between those dominant components sits a much smaller share ordinary matter, the substance of atoms. This ordinary matter is sometimes called baryonic matter. The phrase can sound technical at first, yet the idea is simple. It means the familiar kind of matter made from protons and neutrons, together with the electrons that surround them in atoms. It forms hydrogen and helium in the greatest abundance, then smaller amounts of heavier elements forged later in stars. It gathers into dust, gas, planets, ice, rock, and every structure that seems solid and immediate. Even so, when astronomers total it carefully, they find that ordinary matter makes up only a small fraction of the full cosmic inventory. Across the entire universe, it represents only about 1 part in 20 of the total cosmic energy budget. That result creates an important distinction at the very start of this subject. The missing matter problem discussed here is not the dark matter problem. Dark matter concerns an unseen form of matter inferred from gravity, especially in galaxies and larger structures. The missing matter problem of ordinary matter concerns something more subtle. The expected amount of ordinary matter is known from well-tested models of the early universe, and from several independent lines of observation. Yet for a long time a large fraction of that ordinary matter does not appear where direct observations most easily look. It is not absent from theory. It is absent from straightforward detection. The problem therefore lies less in cosmic existence than in cosmic location. At this widest level, the expectation for ordinary matter comes from the early history of the universe itself. In the first minutes after the hot beginning, simple nuclei form in proportions that depend on how much ordinary matter exists overall. Much later, precise observations of the ancient background light that fills space provide another way to measure the contents of the cosmos. These very different methods, separated by immense spans of time, point toward the same general answer. They indicate a universe with a definite ordinary matter budget. For that reason, when much of the ordinary matter does not show up in nearby surveys of stars and bright gas, astronomers do not conclude that the basic accounting is wrong. They conclude that a great deal of ordinary matter must exist in forms that are hard to see. The visible universe can be misleading in this way. Human sight, and even many telescopes, respond most readily to dense and bright objects. Stars dominate the night sky. Galaxies stand out as islands of light. Yet brightness is not the same as abundance. A small amount of matter under intense conditions can outshine vastly larger amounts spread thinly across enormous volumes. The cosmic scene, therefore, has a built-in bias. It draws attention to luminous concentrations while allowing thin material to fade into near invisibility. A person looking only at the bright structures could easily imagine that the great mass of ordinary matter sits inside stars and the dense regions around them. Careful measurement shows otherwise. Stars contain only a limited fraction of ordinary matter. Gas inside galaxies contains more, and gas around them adds more still. But even after these contributions are counted, a substantial share has long remained untraced. This is why the phrase missing matter can mislead if taken too literally. It does not describe matter that vanishes from the universe. It describes matter that remains physically present while resisting easy detection. It is missing from inventories based mainly on bright emission. It is missing from the regions that attract the eye first. In reality, the universe does not arrange its contents according to human convenience. Much of ordinary matter occupies conditions that are faint, thin, heated, ionized, or spatially extended enough to escape ordinary viewing. The broad cosmic inventory also teaches another quiet lesson. The familiar world is not the typical form of ordinary matter. On Earth, ordinary matter usually appears in condensed forms: solid ground, liquid water, dense air near the surface, biological tissue, metal, and mineral. These forms feel normal because they surround daily life. On the scale of the universe, they are unusual end states, local concentrations within a far more diffuse environment. Most ordinary matter does not spend cosmic time packed into planets or locked into solid bodies. Much of it remains gas, and a considerable portion exists in extremely thin plasma, meaning gas whose atoms have lost one or more electrons. In this state, matter can fill immense volumes while remaining so sparse that almost nothing would be noticed by ordinary human senses. Seen from this widest vantage, the universe becomes a place where emptiness is not truly empty. Vast reaches between obvious structures may appear vacant, yet apparent emptiness can still contain substance spread across distances so large that only collective measurement reveals it. Space is not merely the stage on which matter sits in isolated clusters. Space, on cosmic scales, also holds part of the matter itself in diffuse form. So this opening section remains with the largest view and the simplest conclusion. Ordinary matter is real, limited in total share, and still essential because it forms everything familiar. It is not the dominant substance of the cosmos, yet its expected amount is known well enough that any shortfall becomes meaningful. When astronomers compare the predicted inventory of ordinary matter with the amount plainly visible in stars, galaxies, and other bright structures, the numbers do not fully match. The mismatch does not point to absence, it points to hidden distribution. The universe holds its ordinary matter across scales much larger, thinner, and fainter than first appearances suggest. And the first task is simply to recognize that the cosmic ledger already contains more substance than visible light alone is able to show. Beyond the bright boundaries of galaxies lies a region that appears, at first glance, almost empty. The darkness between one galaxy and another seems like simple absence, a broad separation with little to describe. Yet astronomy shows that this impression is incomplete. Deep space between galaxies contains material, and although that material is extraordinarily thin, it extends across such immense distances that it becomes one of the major reservoirs of ordinary matter in the universe. This realm is called the intergalactic medium. The phrase means, in plain terms, the matter that exists in the space between galaxies. This medium is not a cloud in the familiar sense. it does not resemble the dense white clouds of a planetary sky, nor even the darker gas clouds found inside galaxies where stars form. It is far more rarefied. In many places it is so thin that a volume larger than any human landscape would still contain very little matter by earthly standards. If a person could pass through it directly, there would be almost nothing to feel. Yet over cosmic distances, thinness does not mean insignificance. A substance can be nearly imperceptible in one small region, and still represent an enormous total mass when spread through the vast reaches of intergalactic space. Most of this material consists of the lightest elements. Hydrogen dominates, with helium following behind. These are the primary products of the early universe, and they remain the basic ingredients of ordinary cosmic gas. In the space between galaxies, these elements usually do not sit in neat, neutral atoms alone. Much of the gas is ionized, meaning the electrons are no longer bound tightly to the nuclei. Instead, the gas exists as plasma, a state of matter in which nuclei and electrons move separately. The word plasma can suggest something exotic, but here it simply describes gas that has been energized enough for atoms to come apart. On cosmic scales, plasma is common. The intergalactic medium is therefore not a silent storehouse of cold, dark atoms drifting untouched through perfect emptiness. It is an active environment shaped by radiation, motion, heating, and the long history of structure formation in the universe. Light from galaxies and from energetic sources travels through it. Shock waves from large-scale cosmic growth influence it. Gas can be heated as matter falls under gravity toward larger structures. Material can also be pushed outward from galaxies by stellar explosions and by activity around supermassive black holes. Even when those events begin inside galaxies, their effects do not always remain there. Over immense spans of time, ordinary matter can be driven outward and mixed into the surrounding intergalactic space. Because this medium is so diffuse, it does not present itself easily to telescopes. Dense gas can shine brightly. Dense stars can radiate across vast distances. Thin plasma between galaxies usually does neither in a strong, obvious way. In many regions, it emits too little light for direct imaging. In other regions, it is hot enough and sparse enough that the signals are weak and hard to separate from other sources. The intergalactic medium therefore remains one of those cosmic realities that is more substantial than it looks. It occupies the darkness so broadly that it helps define what deep space truly contains. The environment between galaxies also varies from place to place. It is not uniform like a smooth liquid poured into a container. Some regions are thinner, some denser, some cooler, some hotter. In broad terms, though, it remains a low-density domain where matter is spread across huge volumes. This matters because ordinary human intuition is built in dense surroundings. On Earth, matter usually reveals itself through touch, weight, pressure, opacity, or bright reflection. In intergalactic space, matter may do none of these things in any immediate way. It can be present while remaining almost invisible, not because it is mysterious in composition, but because it is sparse in distribution. Astronomers gradually come to understand that deep space is better imagined not as a perfect void, but as a very thin atmosphere of the cosmos. The comparison has limits, because no sharp boundary encloses it, and no surface lies beneath it. Yet the image is still useful. It helps replace the old picture of absolute emptiness with one of permeating material. Galaxies do not simply hang in nothingness. They are embedded in surrounding matter, and the broader spaces separating them are not blank. Those spaces contain gas that records the history of heating, enrichment, and motion over billions of years. This gas also preserves a kind of simplicity. While planets and stars represent heavily processed matter, shaped by repeated cycles of compression and fusion, much of the intergalactic medium remains closer to the basic ingredients from which later structures grow. Even when it has been altered by nearby galaxies, its dominant character is still that of diffuse hydrogen and helium spread across open space. In that sense, the region between galaxies acts as both reservoir and archive. It holds ordinary matter outside the luminous concentrations, and it preserves evidence of how cosmic environments change with time. For many years, this is precisely where astronomers suspect a large share of the missing ordinary matter must reside. The suspicion does not arise from guesswork alone. It follows from the mismatch between the known cosmic matter budget and the limited amounts seen in stars, cold gas, and other bright galactic components. If ordinary matter is not packed mainly inside visible structures, then the widest remaining home is the immense expanse between them. The intergalactic medium offers that home. Its very faintness explains why the matter remains difficult to count, and its enormous volume explains how so much matter can hide there without ever forming a bright, obvious object. So Section 2 remains in the broad darkness between galaxies and does not move inward yet. It stays with the setting itself, an immense, thin, ionized medium filling deep space. This region seems empty only from a distance, and only to senses trained by bright objects and dense worlds. In physical terms, it is a true component of the universe, made mostly of ordinary matter in its simplest gaseous form. It stretches across the separations that define cosmic scale, holding substance where the eye first sees almost none at all. Across the largest observable scales, ordinary matter between galaxies is not arranged at random. It follows a pattern that astronomy gradually reveals through surveys of galaxies, gas, and the influence of gravity over billions of years. This pattern is known as the cosmic web. The phrase offers a simple image for something vast and delicate matter distributed in long filaments, broad sheets, and denser intersections, with immense voids open in between them. It is not a web in the literal sense, and it has no threads woven by hand. Yet the comparison helps because the universe on large scales shows a connected structure rather than a uniform fog. The basic form emerges from gravity acting over immense time, after the early universe leaves behind its first nearly smooth conditions. Tiny differences in density remain. Some regions contain slightly more matter than others. These differences are small at first, yet gravity amplifies them. Regions with a little more matter pull in additional matter. Regions with a little less matter give up some of what they have. The result is not an instant collapse into isolated objects, but a gradual sorting of matter across enormous distances. Over time, the denser parts become more pronounced, and the less dense parts become emptier. From this slow process comes the large-scale architecture of the cosmic web. In this architecture, filaments are among the most important features. A filament is a long, narrow concentration of matter stretching across immense reaches of space. It contains both dark matter and ordinary matter, though only some of that ordinary matter becomes easy to observe. Gas flows along these filaments under gravity, and the filaments connect larger concentrations in a network that spans the observable universe. Between them lie voids, regions with much lower density. A void is not a perfect vacuum. It still contains some matter, but far less than the filaments and nodes around it. These voids can extend across astonishing distances, making the web appear at once sparse and interconnected. The web is therefore a map of contrast. Matter is not packed everywhere equally. It gathers along preferred paths and leaves great spaces relatively bare. This is one reason missing ordinary matter can remain hard to inventory. If the universe were filled evenly with luminous gas, observation would be simpler. Instead, much of the ordinary matter occupies diffuse structures shaped by gravity into forms that are extended, faint, and uneven. A filament may stretch across enormous volumes, containing a significant share of matter while remaining difficult to see directly because its gas is thin and its light weak. The cosmic web also helps explain why deep space is not merely a collection of isolated galaxies surrounded by emptiness. The larger truth is that structures are linked. Matter moves, heats, and spreads within an environment that has shape on the grandest scales. The web provides channels along which gas can gather and flow. It defines where ordinary matter is more likely to accumulate and where it thins away. Even when the eye sees only scattered points of light, the underlying arrangement is broader and more continuous. This large-scale pattern is not guessed from imagination alone. It is supported by observation and by numerical simulations based on accepted physics. Surveys of galaxy positions reveal clustering that traces the web's broad form. Absorption studies, in which distant light passes through intervening gas, also provide evidence for filamentary matter between brighter objects. Simulations that begin with early density variations and allow gravity to act over cosmic time produce structures that resemble what is observed. In this way, theory and observation reinforce one another. The universe behaves not like a random sprinkling of islands, but like a connected system shaped by gradual growth. Within the web, ordinary matter does not always sit in the same state. Some of it remains relatively cool and diffuse. Some is heated as matter falls into denser regions. Some is ionized by energetic radiation or by shocks associated with structure formation. The common feature is not a single temperature or density, but a shared placement within the web-like framework. Matter occupies filaments, surrounds intersections, and leaves voids comparatively depleted. The ordinary matter that proves hard to find in direct surveys is therefore not thought to be hidden in small secret pockets, scattered arbitrarily through the cosmos. It is thought to be distributed through this large-scale network, often in forms too faint to stand out strongly against the dark. The web also offers a better way to imagine scale. A galaxy, however large it seems, is only one condensed part of a much wider setting. The web extends far beyond any individual bright system. Its filaments can span distances so large that a single structure dwarfs the size of familiar galactic forms. In that sense, the cosmic web is the true outer landscape of ordinary matter. It is the framework within which brighter structures appear, not a decorative background behind them. Because the web is so extended and so thin, it challenges the habits of ordinary observation. Human experience expects important structures to be dense, sharply bounded, and easy to distinguish from their surroundings. The cosmic web is often none of these. Its boundaries are gradual, its matter is diffuse, its visibility is limited, yet its physical importance is immense. It helps determine where matter collects, where it remains sparse, and how the universe organizes itself over the greatest distances available to measurement. In this section, the focus stays with that broad architecture alone. The universe at large is not a featureless expanse with bright objects dropped into it at random. It is a connected terrain of filaments and voids, shaped by gravity from early density differences and filled with ordinary matter spread far beyond the compact regions that shine most brightly. The hidden matter problem belongs naturally to this setting, because the web provides both the location and the conditions that allow large amounts of ordinary material to remain real, widespread, and difficult to count. The darkness between bright structures is therefore not simply empty separation. It is part of an organized cosmic landscape, and that landscape has form. Within the vast pattern of filaments and voids, galaxies appear as the clearest visible anchors. They are the places where ordinary matter becomes concentrated enough to shine strongly, forming recognizable structures that can be mapped across immense distances. Against the faintness of deep space, a galaxy stands out as a coherent object, a gathering of stars, gas, dust, and gravity. It provides shape to the wider cosmic web by marking the denser intersections and strands where matter has collected over long spans of time. When astronomers survey the universe on large scales, galaxies are often the first guides because they're bright enough to detect in large numbers and distant enough to trace the form of cosmic structure. A galaxy is not a single thing, but a system. It contains stars in enormous numbers, along with interstellar gas and dust spread between them. It is held together by gravity and influenced strongly by dark matter, though the present focus remains on the ordinary matter that can be seen or inferred more directly. Some galaxies are grand spirals with rotating disks and bright arms. Some are ellipticals, smoother in appearance and more dominated by older stars. Some are smaller, irregular systems without a settled form. Across this variety, the important point at this stage is simple. Galaxies gather ordinary matter into places where it becomes much easier to notice than in the diffuse expanses between them. This makes galaxies powerful markers, but also potentially misleading ones. Because they are bright and visually distinct, they can seem like the main repositories of ordinary matter in the universe. A person looking at astronomical images might naturally conclude that the visible story is the main story. Bright starlight appears to define cosmic substance. Dust lanes add texture. Gas clouds shine in regions of star formation. All of this is real, yet the brightness of galaxies creates a bias in perception. It suggests that what shines most strongly also contains most of the ordinary matter. Careful accounting shows that this is not so. Stars, for all their brilliance, do not hold the majority of ordinary matter. They represent an important fraction, but not the full one. A galaxy can appear dazzling while still containing only part of its ordinary substance in stars. Gas within galaxies adds another portion, especially hydrogen, which can fill disks, gather into clouds, or remain more diffuse between stellar concentrations. Dust contributes a smaller amount, yet it plays an important role in shaping what galaxies look like by absorbing and scattering light. Even after these visible and semi-visible components are counted, the broader cosmic inventory still indicates that much ordinary matter lies elsewhere or in forms not easily captured by ordinary observation. This is one reason galaxies are called anchors rather than answers. They fix the eye. They provide reference points in a dark and extended universe. They reveal where structure has condensed enough to become luminous. Yet they do not by themselves resolve the full matter budget. Instead, they show where a small but significant share of ordinary matter has become concentrated into bright systems. They are signposts of density, not complete containers of all the ordinary matter that gravity has organized on large scales. Galaxies also preserve a record of transformation. Much of the gas within them does not remain gas forever. Under the right conditions, it cools, condenses, and forms stars. Those stars then alter their surroundings through radiation, winds, and, in some cases, explosive ends. Heavier elements are forged in stellar interiors and redistributed into galactic environments. In this way, galaxies become places where ordinary matter is processed into increasingly complex forms. Hydrogen and helium remain dominant overall, yet within galaxies the history of matter becomes richer. Stars create structure, chemistry, and light. They turn diffuse ingredients into visible systems that can be studied across deep time. Even so, it is important not to let this richness narrow the view too soon. Galaxies are central to observation because they are luminous, but they are only one level of the cosmic arrangement. On the scale of the universe, they're concentrated nodes inside a much broader field of diffuse matter. Their brightness can conceal this fact by making the rest seem secondary. In practice, the opposite is often true. A large volume of dim material can outweigh a smaller volume of bright material. The cosmic eye is drawn to the flame, but the larger reservoir may lie in the surrounding air. When astronomers count ordinary matter within galaxies, they therefore treat visible light with caution. Starlight helps estimate stellar mass, but it does not automatically tell the whole story. Gas must be measured through other methods, and even then, not all phases of gas are equally easy to detect. Dust may obscure parts of the view, distance complicates interpretation. Across large surveys, the combined picture becomes clear enough to establish one broad conclusion. Galaxies contain only a fraction of the ordinary matter expected from the cosmic inventory set by the early universe and confirmed by large-scale observation. This realization changes the role galaxies play in the missing matter problem. At first, they seem like likely storage sites because they are the dominant visible structures. Later, they become measurement points that reveal a shortfall. Their stars can be counted, their internal gas can be estimated, their light can be mapped across cosmic history. Yet once that work is done, the total remains incomplete. The missing share is not likely to be hidden mainly inside the bright stellar populations that define galactic appearance. The visible anchors remain essential, but they also point beyond themselves by showing that the luminous content is not enough. So this section stays with galaxies as visible anchors in the cosmic web. They are the places where ordinary matter becomes bright, structured, and comparatively easy to observe. They trace the denser parts of the universe and provide the clearest map of large-scale structure. They gather stars, gas, and dust into systems with distinct forms and long histories. Yet they do not contain the full ordinary matter account. Their importance lies partly in their incompleteness. By shining so clearly while holding only part of the expected substance, galaxies help reveal that much of ordinary matter remains distributed in less obvious forms beyond the bright concentrations that first define the visible cosmos. Around the visible body of a galaxy lies an outer region that does not shine with the clarity of stars and does not present the sharp form of a spiral arm or a bright central bulge. This region extends far beyond the obvious light and holds a large amount of ordinary matter in gas so diffuse that it is easy to overlook. Astronomers often describe this surrounding domain as a galactic halo. The word halo can suggest a narrow ring of light, yet here it means something broader and more physical, an extended envelope around a galaxy, reaching far outside the main stellar system. Part of that halo consists of dark matter, inferred through gravity, but another important part consists of ordinary gas. It is this gaseous halo that matters in the present region of the story. The gas in these halos is not arranged like the dense gas clouds inside galactic disks. It is usually thinner, hotter, and spread over much greater distances. In many galaxies it forms a vast, nearly invisible atmosphere surrounding the luminous structure within. This gas is not merely a fringe detail, it can contain a substantial portion of a galaxy's ordinary matter. The visible stars may dominate the appearance of a galaxy, and the denser gas within the galaxy may dominate much of its internal activity. Yet the halo adds a broader reservoir that changes the full accounting. When astronomers look beyond the bright edges, they find that galaxies do not end where their starlight fades. Their ordinary matter extends outward into a much larger volume. This halo gas often exists at very high temperature. It is heated by the motion of matter falling into the galaxy's gravitational well, by shocks associated with structure growth, and by energy released from stellar processes and central activity. Under such conditions, atoms may lose electrons and the gas becomes ionized plasma. Because it is spread thinly, it does not radiate in the easy, direct way that dense material often does. Some of it can be detected in X-ray light, especially in larger galaxies and in more massive systems, but the signals are faint and not always complete. In other cases, the gas reveals itself through absorption, where light from a more distant source passes through the halo and carries the imprint of intervening material. These methods help astronomers understand that the halo is real, even when it is not plainly visible in an ordinary image. A useful way to think of this halo is as a galactic atmosphere, though far more extended and tenuous than any planetary one. A planet's atmosphere is dense enough near the surface to scatter light, carry clouds, and exert pressure that bodies can feel. A galactic halo does none of these things in any familiar way. It is too thin and too vast. Yet the comparison still helps because it replaces the idea of a galaxy as a hard-edged object with the more accurate image of a bright inner system immersed in surrounding gas. The stars occupy only the concentrated centre of a much larger domain of ordinary matter. This change in perspective matters because it softens the apparent boundary between galaxies and deep space. From a visual standpoint, a galaxy looks like a distinct island with a visible outline. From a physical standpoint, the transition is more gradual. Gas extends outward, becoming thinner with distance, mingling eventually with the wider environment. The galactic halo therefore occupies an intermediate realm no longer the dense inner galaxy, not yet the fully open intergalactic medium in its broadest sense. It is the outer atmosphere of a galaxy, shaped by both internal history and larger cosmic surroundings. The halo is also a record of exchange. Gas does not simply remain fixed there forever in a static shell. Some material falls inward from the wider cosmic environment, feeding future galactic growth. Some material is pushed outward from the galaxy by stellar winds, exploding stars, and energetic processes near the central black hole. In this way, the halo becomes a circulation zone. Matter enters, matter leaves, matter mixes, cools, heats, and shifts across long spans of time. The bright galaxy at the centre is therefore not a sealed container. It is connected to its halo through continuous transfer. This helps explain why ordinary matter proves so difficult to count if attention remains only on stars and the densest visible gas. A galaxy's bright parts present a partial image of its real extent. The halo, though dim, can contain a major hidden share. That does not mean every galaxy has the same amount of halo gas or the same temperature structure. Galaxies differ in mass, history, environment, and activity. Some hold more hot gas than others. Some lose gas more readily. Some sit in crowded regions where interactions alter their outer material. Even so, the general lesson remains steady. A significant portion of ordinary matter associated with galaxies lives in outer gaseous halos too faint to dominate the view. These halos also influence how galaxies evolve. Gas in the halo can serve as a future supply, gradually cooling and moving inward under the right conditions. At the same time, feedback from the galaxy can keep some halo gas hot and extended, slowing its return. This balance shapes how efficiently galaxies form new stars over cosmic time. The halo is therefore not only a hidden mass reservoir but also an active regulator of galactic life. It stores matter, receives matter, and responds to the energy flowing out from the visible galaxy below it. At this stage of the outer to inner path, the halo becomes an important bridge in the matter story. The previous sections established that much ordinary matter lies beyond the bright stellar content of galaxies, and that the cosmic web provides the larger architecture. Here the focus rests on the wide gaseous envelopes around individual galaxies, where part of that ordinary matter gathers in hot extended form. The eye does not naturally linger there, because the halo lacks the sharp light of stars and the recognizable shape of a galactic disk. Yet physically it is essential. It expands the true size of a galaxy, carries evidence of matter exchange, and reveals that a bright galaxy sits inside a much larger sphere of faint gas. In that quiet outer atmosphere, ordinary matter remains present, substantial, and easy to miss. Beyond the outer halos of galaxies, and often mingling with them at their furthest reach, lies a broader realm of diffuse plasma spread through the larger structures of the universe. This material is not confined neatly inside bright galactic systems, nor does it form compact clouds that stand out sharply against the dark. It occupies extended regions between galaxies, especially along the denser strands of the cosmic web, where ordinary matter has collected without becoming highly condensed. In this state, the missing ordinary matter is not gathered into clear objects. It exists as a broad, faint medium, thinly distributed and difficult to observe directly. This is one of the main environments in which astronomers expect to find the long-sought ordinary matter that earlier inventories failed to locate in stars and denser galactic gas. The gas here is often described as warm-hot plasma. The phrase joins two ideas. It is warm-hot because its temperature is much higher than that of the cold and moderate gas often discussed inside galaxies. It is plasma because many of its atoms no longer hold on to their electrons. A plasma is simply gas in which electrons and atomic nuclei move separately, rather than staying bound together in complete atoms. In ordinary daily life, matter usually appears in solid, liquid, or familiar gas form. On cosmic scales, plasma is extremely common. In the diffuse regions between and around galaxies, it becomes one of the natural states of ordinary matter. This plasma is mostly made of hydrogen and helium, the same basic ingredients that dominate ordinary matter across the universe. The difference lies not in composition, but in condition. Here the gas is spread thinly and heated enough that atoms are partly or largely ionized. It does not gather into the dense, cool clouds that would block light strongly, or produce obvious bright emission in simple images. Instead, it forms vast, rarefied reservoirs, often stretched along filaments of the cosmic web and around galaxy groups and clusters. A small amount occupies any one local volume, but the total across cosmic distances becomes enormous. Several processes help create and maintain this state. Gravity is one of the most important. As matter falls into the growing structures of the universe, motion is converted into heat. Gas streaming into denser regions can be shocked and warmed as it slows and compresses. galaxies also contribute. Energetic events inside them can push material outward into the surrounding environment. Stellar explosions, strong winds from stars, and activity near central supermassive black holes can all send gas beyond the bright galactic body. Over long stretches of time, this outward flow mixes with the wider medium between galaxies. The diffuse plasma of deep space is therefore both primordial and processed. It retains the basic simplicity of hydrogen and helium, while also carrying the imprint of cosmic heating and galactic exchange. The difficulty is not imagining that such gas exists. The difficulty is seeing it clearly. Dense matter reveals itself with comparative ease. A star glows intensely because enormous energy is released from a compact region. A dense gas cloud can absorb or emit light in ways that stand out strongly. Diffuse plasma does not behave so helpfully. Its thinness means that even if it is hot, the total light emitted from any small portion may be weak. The gas may shine in X-ray light under some conditions, but often too faintly for easy mapping. In other situations, it leaves subtle absorption signatures in the light of more distant objects. Yet those signatures can be sparse and difficult to assemble into a full census. The matter is real, but its low density makes its presence hard to convert into a complete picture. A useful image is that of an ocean, though only in the sense of extent, not density. An earthly ocean presses, flows, reflects, and surrounds with unmistakable presence. This cosmic ocean does none of those things at human scale. It is far too thin, yet like an ocean, it spreads over a vast domain, occupying a large connected environment rather than remaining trapped in isolated pockets. It surrounds brighter structures, fills the spaces between them, and holds more material in total than its quiet appearance first suggests. In that sense, the comparison helps. It reminds the mind that great reservoirs do not always announce themselves with sharp edges or obvious brightness. This diffuse plasma also changes how deep space itself must be imagined. Empty-looking intergalactic regions are not simply gaps. They're environments with temperature, ionization, motion, and history. Matter in these regions is not at rest in a perfect stillness. It flows gradually under gravity, responds to energetic disturbances, and participates in the broader evolution of cosmic structure. Even when it remains nearly invisible, it is part of the living physical medium of the universe. For the missing matter problem, this region is especially important because it offers both scale and concealment at once. To hide a large fraction of ordinary matter, the universe does not need secret compact objects scattered in darkness. It only needs ordinary gas distributed through immense volumes in a state difficult to detect. Diffuse plasma provides exactly those conditions. It preserves the known matter budget while evading simple observation. The matter is not missing from space. It is missing from easy visibility. The broad picture that emerges here is quiet but decisive. Bright galaxies and their stars do not define the full extent of ordinary matter. Around them and between them lies a much larger volume filled with hot, ionized, rarefied gas. This medium is not spectacular to the eye. It rarely forms the kind of image that captures immediate attention. Yet in physical importance it is profound. It may contain a substantial share of the ordinary matter that the cosmic inventory requires. It turns the darkness between bright objects into a material environment rather than a vacant separation. So this section remains in that wide region of diffuse plasma alone. It does not move yet to the problem of why the gas is so difficult to detect in practice, nor to the special signals that later help measure it. For now, the focus stays with the environment itself, warm, hot, ionized, extended ordinary matter spread around and between galaxies, following the large-scale structure of the universe. In this thin plasma ocean, the missing ordinary matter is not lost in any dramatic sense. It is simply dispersed across a realm so broad and so faint that its true abundance only becomes clear when the cosmos is viewed as a whole. The ordinary matter hidden in diffuse plasma remains difficult to detect for a reason, rooted less in mystery than in method. Matter becomes easy to observe when it is concentrated, bright, cool enough to form clear atomic signatures, or placed in front of a strong background light. The missing ordinary matter in deep space often satisfies none of these conditions. It is spread thinly across enormous volumes. It can be hot, ionized, and nearly transparent. It can emit very little light from any one region, while still amounting to a large total mass when taken across cosmic distances. The challenge, therefore, lies in the difference between abundance and visibility. A great deal of matter can exist while producing only weak observational traces. Human intuition is poorly trained for this kind of environment. In daily experience, more matter usually means a stronger signal. A thicker wall blocks more light. A denser cloud looks more opaque. A heavier object presses more firmly on the hand or ground. In cosmic settings, this expectation often fails. A vast region of extremely thin gas may contain more total matter than a bright, compact object, yet still remain far harder to notice. The reason is that telescopes do not respond directly to total mass in a simple way. They respond to radiation, absorption, motion, and other measurable effects. If matter is spread too thinly, those effects may become weak even when the total amount of material is large. Light itself helps explain the problem. Dense matter can produce strong emission because many particles occupy a small region and interact often. In a very diffuse medium, particles are far apart, collisions are rarer, emission can be faint. Even hot gas may not shine strongly enough to stand out clearly, unless it is either sufficiently dense or observed with instruments sensitive enough to detect weak signals. Some of the diffuse plasma thought to contain missing ordinary matter does emit in X-ray light, yet that emission is often dim and difficult to map over large regions. The signal can blend with other sources, remain below detection thresholds, or appear only in exceptional environments where the gas is denser than average. Temperature complicates the picture further. Cold gas can reveal itself through certain spectral lines, which are specific fingerprints of atoms and molecules. Very hot gas behaves differently. If it is also thin, some of the usual observational handles weaken. Ionized atoms no longer produce the same patterns as neutral ones. Electrons move freely. The gas becomes more transparent in ordinary visible light. To detect it, astronomers often need either sensitive instruments operating at wavelengths beyond human sight or favorable alignments in which the gas affects light from something behind it. Even then, the measurements can be partial. They may reveal one temperature range better than another, or one environment better than another. Distance adds another layer of difficulty. The missing ordinary matter is not hidden in a nearby laboratory. It lies across vast reaches of space, where signals weaken during travel and where many structures overlap along the line of sight. A faint trace from diffuse gas may be mixed with contributions from a galaxy, a halo, a cluster, or the Milky Way itself. Sorting these layers requires care. A telescope may receive a single blended record from several regions at once. Untangling which portion belongs to the diffuse medium between galaxies is often a subtle task rather than a direct one. The geometry of the gas also matters. If matter gathers into compact shapes, observers can point a telescope at a clear target. Diffuse cosmic plasma is different. It spreads through filaments, outer halos, and broad intergalactic regions with gradual boundaries. This makes it hard to define where one structure begins and another ends. The sky does not always present a neat outline around the hidden matter. Instead, it offers faint transitions and overlapping environments. A survey can therefore miss part of the matter simply because the matter does not arrange itself into sharply bounded objects. Another source of difficulty comes from contrast. Bright astronomical sources dominate attention and detection. A galaxy full of stars can outshine the thin gas around it. Energetic galactic centers can flood observations with radiation that masks weaker surrounding signals. Even the instruments themselves must work against background noise, detector limits, and contamination from other cosmic sources. The hidden matter is not only faint on its own terms, it often sits near or along sight lines crowded by brighter phenomena. This is why the missing matter problem remains stubborn for so long, even after the cosmic inventory points clearly toward its existence. The theoretical side tells astronomers that ordinary matter should add up to a certain amount. The observational side easily captures only part of that amount. The missing share is not concealed by a single dramatic barrier. It is concealed by a combination of low density, high ionization, weak emission, immense distance, gradual structure, and competition from brighter foreground and background sources. No single obstacle is impossible. Yet together they make a large fraction of ordinary matter difficult to count directly. A useful comparison is mist over a huge landscape at dusk. A nearby dense object can be seen plainly, but a very thin layer spread over a vast area may alter the scene only slightly. It is present everywhere, yet hard to isolate. Its total amount may be substantial, but no one small patch announces it strongly. The comparison is imperfect because cosmic plasma is far thinner than mist and behaves according to different physics. Yet it clarifies the observational challenge. Presence does not guarantee prominence. Astronomy therefore learns an important discipline from this problem. It cannot rely only on what glows brightly. It must also infer matter from subtle effects, from integrated signals gathered over long distances, and from methods sensitive to environments too faint for ordinary imaging. The hidden ordinary matter teaches that the universe often stores its substance in forms that are physically ordinary but observationally difficult. The challenge is not to invent exotic explanations too quickly. The challenge is to measure the faint. So this section remains entirely with the reason the matter stays hidden. It is diffuse rather than condensed, often ionized rather than neutral, extended rather than bounded, and faint rather than bright. Its emission is weak, its structure is gradual, and its signals are often entangled with other cosmic layers. The missing ordinary matter problem persists for so long not because the matter behaves strangely, but because deep space rewards methods capable of reading extremely subtle traces. In the darkness between bright structures, ordinary matter hides in plain sight by being too thin, too spread out, and too quiet for easy observation. Into this broad and quiet setting comes a very different kind of phenomenon, a fast radio burst. The name is compact and descriptive. A burst is a sudden release of energy. Radio refers to the long wavelength part of the electromagnetic spectrum, far beyond human sight. Fast means exactly what it suggests. The event is brief. lasting only a tiny fraction of ordinary human time. A fast radio burst, often shortened to FRB, is therefore a short flash of radio energy arriving from deep space. It appears suddenly, is recorded by radio telescopes, and is gone almost at once. The first impression of such an event is one of extreme brevity. A signal travels across an immense cosmic distance, yet the moment of arrival at the telescope may last only milliseconds. In that short interval, the burst stands out sharply against the quieter radio background. Then it fades. Nothing in ordinary daily experience prepares the mind for this combination of scale and speed. The journey belongs to the largest distances in astronomy. The arrival belongs to a moment shorter than a blink. That contrast is part of what gives fast radio bursts their scientific importance. A very small event in time carries evidence from a very large span of space. Radio astronomy is the field that makes these arrivals visible. Human eyes cannot detect radio waves. Special instruments are required to gather them, separate them by frequency, and record how their intensity changes with time. A radio telescope does not produce a simple picture in the same way an optical telescope often does. Instead, it listens to patterns in electromagnetic radiation arriving from the sky. When a fast radio burst appears, it enters that listening system as a sudden, structured spike. The burst is not seen as a flash in visible light. It is detected as radio energy reaching the instrument from a particular direction. This kind of arrival is unusual, not only because it is brief, but because it is powerful. In an instant measured in milliseconds, an FRB can release an extraordinary amount of energy in radio wavelengths. The burst is so strong that it can be detected even after crossing vast reaches of the universe. That does not mean it lights the sky in a familiar sense. It remains a radio event, invisible to ordinary sight. Yet by the standards of radio astronomy, it is intense. The signal must be, because the distance is immense and the path through space is long. A weak event would vanish beneath noise long before reaching Earth. The bursts that are recorded therefore announce themselves not through long duration, but through concentrated signal. The arrival of an FRB also has a certain unpredictability. Many bursts are one-time detections from the point of view of the observer. A telescope catches the signal, records it, and cannot simply wait for the exact same flash to happen again in the same form. Some FRB sources do repeat, and that repeating behavior becomes an important part of modern study. But the general experience of detection still carries an element of surprise. The sky is monitored, data stream continuously, and then, for a tiny moment, a distant burst cuts through the background. The event is short enough that discovery depends not on leisurely observation, but on constant readiness and careful signal analysis. This is one reason FRBs remain difficult to study despite their power. Their strength does not make them easy in every sense. A signal that lasts only milliseconds leaves very little time in which to capture detail. Instruments must already be operating, already collecting data, and already capable of identifying a burst in the flood of incoming radio information. The challenge is therefore not only to detect a faint thing, it is to detect a brief thing. Time itself becomes part of the difficulty. As more FRBs are found, a broader picture begins to emerge. They are not local features of the solar system, nor ordinary atmospheric events, nor signals confined to the Milky Way alone. Observations indicate that many come from far beyond our galaxy. Some have been traced to distant host galaxies, confirming their extragalactic nature. This changes the scale of their meaning immediately. A short radio flash is no longer just an odd signal in the sky. It becomes a message carried across intergalactic distance. The arrival at Earth is the final instant of a journey that begins in another galaxy, sometimes billions of years in the past. That deep origin makes the moment of detection feel almost compressed, as though a vast history narrows into a single brief crossing at the telescope. The burst enters the receivers, is separated into its component frequencies, and is stored as data. From the ground, the event seems tiny. In reality, it belongs to the grand setting established by the earlier sections, the cosmic web, the intergalactic medium, the halos of galaxies, and the diffuse plasma of deep space. The FRB is not part of those environments in the same quiet sense that gas is. It is a moving signal, a flash passing through them. Its arrival brings sudden clarity into a domain otherwise dominated by faintness. The history of FRB research also reflects this suddenness. The field begins with the recognition that unusual, very brief radio pulses are appearing in the data. At first, there is caution. Rare signals in radio astronomy must be checked carefully, because terrestrial interference can mimic celestial events. Over time, repeated detections from different instruments and from different directions establish that FRBs are genuine astronomical phenomena. The field grows quickly as new telescopes and improved search methods reveal more bursts. What begins as an odd and isolated kind of detection becomes a recognized class of cosmic event. Even at this stage, an important balance remains. Much has been learned, but not everything is settled. Observations indicate that FRBs can arise from more than one kind of environment, and it remains uncertain whether all bursts come from the same kind of source. Some repeat, some do not repeat in any observed way. Some are found in galaxies with active star formation, while others appear in different settings. Yet despite these open questions, their basic observational identity is clear. They are brief radio flashes from deep space, powerful enough to be detected across enormous distances, and short enough that their arrival is recorded as a sudden transient event. So this section remains with the arrival itself, in a universe where much ordinary matter stays faint and spread out. The FRB enters as something bright in radio terms, brief in time and distant in origin. It is not a steady beacon. It is a flash. It does not fill the sky. It appears for milliseconds. Yet in that tiny interval, a path across the deep cosmos reaches the telescope and becomes measurable. The signal enters quietly, not to dominate the heavens, but to cut through them for an instant with enough force to be noticed. In the study of hidden matter, that moment of arrival changes everything simply by existing as a precise flash from far beyond the Milky Way. A fast radio burst arrives from far beyond the Milky Way, and that fact immediately places its source inside another galactic setting. The burst does not emerge from featureless emptiness. It begins in a real environment shaped by stars, gas, magnetic fields, gravity, and the local history of a host galaxy. Once astronomers localize a burst well enough to connect it with a specific distant galaxy, the event stops being only a brief signal in the sky. It becomes part of a larger astrophysical landscape. The host galaxy provides the surrounding region in which the burst source lives, evolves, and releases its radio flash. This host environment matters because location carries meaning. A burst found in a galaxy with active star formation points toward one kind of local history. A burst found in a more mature galactic population suggests another. A burst close to a bright star-forming knot differs in interpretive weight from a burst placed far out in a quieter region of its host. the position does not solve the source immediately, but it narrows the field. In astronomy, environment often acts as evidence. It reveals what kinds of objects are likely to be present and what physical conditions surround them. Observations now show that FRBs inhabit more than one kind of host galaxy. Some are traced to small galaxies rich in recent star formation. Some are linked to larger, more massive galaxies. Some repeating bursts are found in active environments associated with strong local magnetism and persistent radio emission. Others appear in settings that seem less extreme. This diversity is important because it prevents the story from becoming too narrow. The evidence does not support a single simple picture in which every FRB comes from the exact same kind of host and the exact same local neighborhood. Instead, the host galaxies indicate a family of environments with some common themes and some notable differences. One common theme is youth in the astrophysical sense. Many FRB environments appear compatible with the presence of highly magnetized neutron stars known as magnetars. A magnetar is a compact stellar remnant with an extremely strong magnetic field. It forms after the collapse of a massive star or through other channels that create a dense neutron star under unusual conditions. Magnetars are leading candidates for at least some FRB sources because they are energetic, compact, and capable of violent magnetic activity. The association of an FRB-like signal with a galactic magnetar strengthens this idea by showing that magnetars can produce radio bursts with the right general character, even though the full extragalactic population may not reduce to one exact mechanism. The host galaxies help support this possibility. Star-forming regions are places where massive stars are born, live short lives, and end as neutron stars or black holes. If at least some FRBs arise from young magnetars, then a connection to star-forming environments is natural. Several well-studied repeating sources fit comfortably within that broad expectation. They are found in galaxies and local regions where young energetic remnants are plausible. In some cases, a repeating FRB is also associated with a persistent radio source, suggesting a complex local environment shaped by ongoing energetic activity. That kind of neighborhood fits the idea of a compact engine embedded in surrounding material rather than an isolated event occurring in a clean vacuum. Yet the host galaxy picture is not uniform enough to close the case completely. Some localized FRBs come from larger, more mature galaxies that do not immediately suggest only the youngest stellar populations. This broadens the possibilities. It may mean that magnetars can arise through more than one formation path. It may also mean that more than one kind of object can generate FRBs. Observations indicate that repeating and apparently non-repeating bursts may not always share identical properties, and it remains uncertain whether all FRBs belong to one physical class expressed in different ways, or to several related classes produced by different engines. The host galaxies do not erase that uncertainty, they define it more clearly. This is one reason the local galactic setting matters so much. A burst source does not need to announce its identity directly if its environment already limits what is plausible. A compact object born from recent stellar death is more at home in one type of region than another. A long-delayed merger event would have a different environmental pattern. A source surrounded by dense ionized gas and strong magnetic influence leaves different clues from a source located in a comparatively calm outer region, by studying where FRBs appear inside their hosts. Astronomers move from broad speculation toward evidence-based inference. The host galaxies also reveal that FRBs are not confined to a rare and singular corner of the universe. They occur across cosmological distance and across a range of galactic settings. This tells astronomers that whatever powers them must be capable of appearing in many parts of cosmic history. Some localized bursts come from epochs when the universe is much younger than it is now. Others arise in closer and more recent settings. The phenomenon therefore belongs not to one isolated galactic age, but to conditions that recur across time. The host galaxy acts as the local frame for each burst, while the growing sample of hosts shows that the phenomenon is widespread across the larger universe. At the same time, the host is not always the whole environment. A galaxy may be the larger home, yet the immediate neighborhood of the source can be more specific. A burst might come from a star-forming region, from the outskirts of a galaxy, from a dense local plasma environment, or from a site influenced by earlier explosive activity. The galaxy tells part of the story, and the local site inside it tells more. This layered context is essential. A spiral galaxy by itself does not produce an FRB. A particular compact source inside that galaxy does. The host therefore acts as a setting that frames the probable source rather than replacing it. What emerges from this region of the story is a careful balance. Observations indicate that FRBs are extragalactic, and that many can be tied to specific host galaxies. Those hosts are diverse but not meaningless. Their properties support the view that compact energetic remnants, especially magnetars, are leading explanations for at least part of the FRB population. Repeating sources in particular often fit naturally within magnetar-rich interpretations. At the same time, the observed variety of host types and local placements leaves room for more than one pathway. It remains uncertain whether all FRBs share one origin, or whether the category includes several engines capable of producing similar radio flashes. So this section stays with the distant galactic homes alone. The burst begins somewhere inside another galaxy, inside a real astrophysical environment shaped by stellar birth, stellar death, gas, magnetism, and time. The host galaxy does not merely supply a background image, it provides evidence. It shows that the FRB source belongs to the material life of galaxies and not to abstract empty space. In those remote galactic settings, the flash has a birthplace, and the character of that birthplace begins to reveal what kind of object may be responsible for the brief radio signal that later reaches across the universe. Once a fast radio burst leaves its source region inside a distant galaxy, it begins a long passage through matter that is almost invisible. The burst itself is not a material object moving through space like a stone through water. It is a pulse of electromagnetic radiation, a travelling pattern of electric and magnetic fields. In empty space, such radiation moves at the speed of light. Yet the universe between galaxies is not perfectly empty. It contains thin plasma, and that plasma matters because the burst must cross it on the way to Earth. The path is long, the medium is sparse, and the interaction is gentle. But across immense distance, even a gentle interaction becomes important. This journey begins in the burst's local environment. The radio pulse first passes through the material near its source, then through the wider region of its host galaxy, then through the galaxy's outer halo. After that, much of its path lies in the intergalactic medium, where diffuse ionized gas stretches along large-scale cosmic structure. The burst may also cross halos of other galaxies, pass through denser parts of filaments, or travel across more rarefied regions nearer cosmic voids. Each part of the route adds its own small influence. None needs to block the burst completely. A slight effect, repeated across enormous reaches, is enough. The crucial component in this medium is the free electron. A free electron is simply an electron no longer bound tightly inside an atom. In ionized gas, Electrons and nuclei move separately, and the electrons can respond easily to passing electromagnetic waves. Radio waves are especially useful in this setting because they are sensitive to the presence of these free electrons. As the burst travels through plasma, the oscillating electric field of the radio signal causes the electrons in the medium to respond. The electrons do not carry the burst away or absorb it entirely under ordinary intergalactic conditions. Instead, they influence how the wave moves through the medium. This is a subtle kind of interaction. Deep space plasma is so thin that the burst still crosses it with remarkable success. The signal is not smothered. It arrives after a journey of vast distance, often from a source billions of light years away. That alone shows how transparent much of the route must be. Yet transparency does not mean indifference. A clear medium can still alter a passing wave slightly. The radio pulse travels through a kind of cosmic fog, one so thin that it is almost nothing by human standards, but not nothing in physical terms. The burst carries the memory of that crossing. The effect depends on the fact that the radio pulse is not just one single pure tone. It contains a range of radio frequencies. In empty vacuum, those components would remain aligned in time as they travel, preserving the burst's sharp arrival. In plasma, the different frequencies do not all behave in exactly the same way. The presence of free electrons causes the lower frequency parts of the signal to respond differently from the higher frequency parts. The result is not chaos, but a structured stretching of the burst in time. What begins as a compact pulse at the source becomes a more spread arrival by the time it reaches the telescope. At this stage, the important idea is physical rather than mathematical. The radio wave and the plasma are not strangers passing without contact. The wave enters a medium containing mobile charges, and those charges respond. Because of that response, the pulse no longer behaves exactly as it would in a perfect vacuum. The interaction is tiny at every small step along the route, but the path is so long that the tiny effects accumulate. The universe itself becomes part of the signal's journey. The burst is not merely emitted in one place and received in another, it is shaped along the way. This shaping is especially valuable because free electrons are widespread in the very matter that proves hardest to see directly. The ordinary matter hidden in intergalactic space often exists as ionized plasma. That means it naturally contains the free electrons capable of influencing radio waves. A fast radio burst therefore does something unusual. It crosses the very material astronomers are trying to study, and while doing so it acquires a subtle imprint of that material. The burst does not need to stop in the plasma or light it up dramatically, it only needs to pass through it. The journey across intergalactic space is therefore not just long in distance, it is rich in physical contact. Every region of plasma along the line of sight contributes something. Denser regions contribute more. Thinner regions contribute less. A path that crosses galactic halos, filamentary gas, and wider diffuse plasma collects the combined influence of all those layers. The radio pulse becomes, in effect, a traveller that records the presence of ionized matter by the way its own internal timing is altered. Because this interaction depends on free electrons, it connects directly to ordinary matter rather than to dark matter. Dark matter shapes cosmic structure through gravity, but it does not couple to light in the same direct way. The burst therefore responds to the ionized ordinary matter along its route. This makes the signal especially valuable in a universe where the missing component is not the total mass of all matter, but the hard-to-find share of ordinary baryonic matter spread through deep space. The pulse is sensitive to the right ingredient. The crossing also preserves a kind of honesty. The intergalactic medium may be faint and difficult to image, but it cannot completely hide from a signal that must move through it. The burst does not ask the gas to glow. It does not depend on the gas forming a bright object. It only depends on the gas existing as plasma with free electrons. Since that condition is already met in much of deep cosmic space, the long route itself becomes useful. Greater distance can even help, because a longer path offers more opportunity for the medium to leave its mark. So this section remains with the passage alone. A fast radio burst leaves a distant galactic environment and travels across the wide plasma-filled regions between galaxies. Along that route, free electrons in ionized gas respond to the wave and alter its passage in a slight but cumulative way. The pulse still reaches Earth because the cosmos is largely transparent to radio waves, yet it arrives changed by the medium it has crossed. In that quiet interaction between travelling radiolight and diffuse plasma, deep space ceases to be passive emptiness. It becomes an active part of the burst story, shaping the signal as it moves across the hidden ordinary matter spread through the universe. A fast radio burst does not arrive at a radio telescope as a perfectly undisturbed flash. By the time the signal reaches Earth, its different radio frequencies no longer land at exactly the same moment. The higher frequency parts of the burst arrive first. The lower frequency parts arrive slightly later. This separation in arrival time is called dispersion. The word is simple in meaning. It refers to a pulse being spread out because different parts of it travel through a medium in different ways. In the case of FRBs, dispersion becomes one of the most important clues in the study of missing ordinary matter. The effect begins with the plasma through which the burst travels. Plasma contains free electrons, and those electrons respond to passing radio waves. Because radio waves of different frequencies interact with the plasma in slightly different ways, they do not all move through it at exactly the same effective speed. In a perfect vacuum, all parts of the signal would remain aligned. In ionized cosmic gas, they do not. The lower frequency waves are delayed more than the higher frequency waves. The burst therefore reaches the telescope as a signal whose components have been gently sorted by frequency during their long journey through space. This sorting is not random. It follows a clear and predictable pattern. When astronomers examine the recorded signal, they see that the radio burst sweeps downward in frequency with time. The upper frequencies arrive first, followed by progressively lower frequencies. The delay may last only a fraction of a second, yet that brief stretch carries evidence from billions of light years of travel. The burst begins as a compact event and becomes, by arrival, a structured trail of timing differences. The medium between galaxies leaves its signature not by stopping the pulse, but by slowing parts of it unequally. A useful image is that of footsteps across different terrain, though only as a loose comparison. A traveller crossing firm ground keeps a steady pace. A traveller crossing softer ground slows slightly. The radio burst behaves in a somewhat similar way as it moves through plasma. Lower frequencies are held back more. Higher frequencies pass with less delay. The comparison has limits, because radio waves and particles obey different physics. Yet it helps show that the signal becomes a record of the medium it crosses. What makes dispersion so powerful is that the effect depends on free electrons. The delay does not arise mainly from starlight or from the gravitational pull of dark matter. It arises from charged ordinary matter in ionized form. Every region of plasma along the line of sight contributes to the total delay. A small contribution may come from the burst's local environment. More may come from the host galaxy, the host halo, the intergalactic medium, intervening halos, and the Milky Way. The observed dispersion is therefore cumulative. It is the sum of many small encounters with free electrons spread along the burst's path. This makes the delay a direct sign that deep space is materially occupied. If the path from the distant burst to Earth were a pure vacuum with no ionized matter, the signal would not show this same frequency-dependent stretching. The ordered lag of low frequencies would be absent. The very existence of the delayed sweep tells astronomers that the burst has crossed plasma. More than that, the size of the effect indicates that the amount of plasma encountered is substantial. The signal behaves as though it has crossed a long route through widespread ionized matter. The hidden matter does not need to announce itself with bright light or dramatic absorption. It only needs to be there as free electrons distributed through space. The FRB supplies the pulse, the plasma supplies the delay, the telescope records the result. In this way, dispersion turns a nearly invisible cosmic medium into something measurable through timing alone. Instead of asking the gas to glow strongly enough for direct imaging, astronomers read the shape of a passing signal and infer the presence of the material that altered it. The effect is also striking because of its consistency. Once an FRB is detected, the arrival pattern across frequency usually reveals dispersion clearly enough that it becomes one of the defining features of the burst. It helps distinguish a real celestial signal from many forms of terrestrial interference. Earthly radio contamination often fails to reproduce the precise dispersive signature expected from a pulse that has travelled through cosmic plasma. The delay itself remains small, but that smallness is deceptive. A fraction of a second seems trivial beside cosmic time, yet it is exactly the kind of subtle effect that deep space produces. The intergalactic medium is thin. Its influence on any one short segment of the path is tiny. Only because the route is so long does the delay become measurable. That is why FRBs are so well suited to this work. They begin as extremely brief signals, giving astronomers a sharp time marker. Dispersion also changes the role of distance in observation. Usually, great distance makes things harder to study because signals fade. Here distance becomes part of the advantage. A longer journey means more plasma can contribute to the delay. The farther the burst has travelled, the more opportunity the hidden ordinary matter has had to leave its mark. Distance still presents challenges, but it also turns the universe into a larger measuring column. The burst samples the matter between galaxies simply by crossing it. For the missing matter problem, this is a quiet turning point. The hidden ordinary matter no longer remains merely suspected because of a mismatch in large-scale accounting. It begins to reveal itself through an effect carried inside the signal of the FRB. The delayed arrival of lower frequencies is the physical response expected when radio waves move through ionized matter. The observation does not yet sort every layer of the path in detail, but it shows unmistakably that the path contains the very kind of charged material that had proven so hard to detect directly. So this section stays with dispersion alone. An FRB reaches Earth with its higher frequencies leading and its lower frequencies trailing behind. That ordered delay arises because free electrons in plasma influence the passage of the radio wave. The more ionized matter along the route, the greater the cumulative delay. In that simple pattern, deep space ceases to appear empty. Its hidden charged matter becomes readable through time itself. The burst is still a flash, still brief, still distant. Yet its stretched arrival quietly declares that the darkness between galaxies is filled with enough ordinary plasma to slow a signal on its way across the universe. Once the delayed sweep of a fast radio burst is recorded, astronomers can do more than note that plasma lies along the path. They can estimate how much ionized ordinary matter the signal has crossed. The key quantity is called the dispersion measure. The phrase sounds technical, yet its meaning is direct. It is a way of expressing the total amount of free electrons lined up between the burst and the observer, not the total mass in all directions, and not the density at one single point, but the accumulated electron content along one narrow path through space. In plain terms, it tells how many free electrons the burst encounters on its journey. This idea is easier to grasp when imagined as a column rather than as a full three-dimensional volume. A radio burst travels along a line of sight. Everything that matters for the delay lies along that line. If the path crosses a short region of dense plasma, that region contributes to the total. If it crosses a very long region of thin plasma, that region also contributes. Both count, because the dispersion measure adds up the influence of free electrons all along the route. A dense segment can matter a great deal over a short distance. A diffuse segment can matter greatly over a vast distance. The final result is cumulative. This is why the delay in arrival time becomes more than a curiosity. It is not merely evidence that some plasma exists somewhere between the source and Earth. It is a measurable effect that can be translated into a column of electrons. The physics of how radio waves move through plasma is well understood, because the lower frequencies are delayed more than the higher ones in a predictable way. Astronomers can fit the observed sweep across frequency and calculate the corresponding electron content required to produce it. The burst becomes a timing tool. Its structure in frequency and time carries enough information to estimate the total free electron column along the path. What makes this especially powerful is that the estimate does not depend on the gas being bright. The hidden ordinary matter in deep space often remains too faint for direct imaging, yet it still contains free electrons, and those electrons still affect the signal. A radio burst passing through, that material acquires a measurable delay whether the gas glows strongly or not. In this way, the dispersion measure turns nearly invisible plasma into something countable. The method does not weigh the gas by collecting its light. It weighs the gas by reading its influence on a passing pulse. The quantity itself is not a direct count of atoms in the everyday sense. It is a count of free electrons projected along the line of sight. That distinction matters because the gas is ionized. In neutral gas, electrons remain bound within atoms and do not affect radio waves in the same way. In plasma, electrons move freely and respond to the electromagnetic field of the burst. Since hydrogen, the most abundant element, contributes one electron when ionized, and helium contributes electrons according to its ionization state, the measured free electron column becomes a practical tracer of the ordinary ionized matter along the route. It is not every detail of the gas, but it is a strong and direct handle on its presence. A useful comparison is rainfall collected in a narrow gauge. The gauge does not reveal the full weather pattern over an entire continent. It records what falls through one vertical column at one place. The dispersion measure behaves similarly, though with different physics. It does not map the whole universe in one observation. It records the integrated electron content through one cosmic line of sight. Each burst offers one such column. A single column is informative. Many columns, taken from many directions and distances, become a powerful survey of the hidden ionized matter in the cosmos. The method also benefits from the shortness of FRBs themselves. Because the bursts begin as extremely brief events, even small delays across radio frequencies remain visible. A broad, slowly varying signal would blur the effect. A fast burst preserves it. The sharper the intrinsic pulse, the cleaner the timing information. This is one reason FRBs prove so valuable compared with many other distant sources. They provide bright, brief, well-timed signals that turn the subtle influence of plasma into an observable pattern. There is also an important conceptual shift here. Earlier sections describe a problem of missing ordinary matter as a mismatch in cosmic accounting. The dispersion measure converts that broad problem into a local reading taken along an actual path, instead of asking only where the matter ought to be in theory. Astronomers begin to measure how much ionized material a real signal has crossed in practice. The hidden matter becomes less abstract. It leaves a numeric imprint on the burst. The universe no longer appears to conceal its ordinary matter completely. It reveals that matter through accumulated delay. This accumulation includes every free electron region along the route. Dense local environments contribute. More diffuse outer halos contribute. The broad intergalactic medium contributes over immense distances. The value measured at the telescope is therefore a total path integral in physical terms, though it can be described more simply as the summed electron column. The signal reaches Earth carrying the combined influence of all the ionized matter it has crossed. That total is exactly what makes the measurement useful. Even if no single region dominates the view in brightness, the burst cannot avoid collecting their combined effect. The translation from delay to electron column also shows why FRBs become known as probes of the cosmic medium. A probe is something that tests or samples a region. The burst does this naturally. It is emitted far away, passes through deep space, and arrives altered in a measurable way. Its dispersion measure is the record of that sampling. One burst samples one route. Many bursts sample many routes. Taken together, they allow astronomers to estimate how ordinary ionized matter is distributed across the universe. At this stage, the power of the method lies in its restraint. It does not claim to reveal every physical property of the gas at once. It does not immediately give full temperature maps, detailed chemistry, or exact three-dimensional shapes. What it provides is something more fundamental for the missing matter problem: the total free electron content along a line of sight. That alone is enough to move from suspicion to measurement. The hidden ordinary matter becomes measurable because it leaves a precise timing signature that can be converted into an electron census along the burst's path. So this section remains with that single measurement step. The delayed arrival of different radio frequencies is used to calculate the dispersion measure, which expresses the total column of free electrons between the source and the observer. Since those free electrons live in ionized ordinary matter, the measurement becomes a practical way to estimate how much hidden plasma the burst has crossed. A brief flash from a distant galaxy thus becomes an electron counter on the scale of the universe. In the quiet mathematics of timing, deep space yields a tally of matter that light alone seldom shows. The dispersion measure of a fast radio burst provides a total column of free electrons along the entire route from source to observer. That total is powerful, but it is not yet the quantity astronomers want most for the missing matter problem. The goal is not simply to know how much ionized matter lies everywhere along the path. The goal is to isolate the share that belongs to the deep regions between galaxies. To do that, astronomers must separate the layers of the journey. The measured delay includes contributions from the Milky Way, from the space around the Milky Way, from the burst's host galaxy, from the source's immediate environment, and from the intergalactic medium in between. The observed value is one total, but the physical path is made of parts. This makes the problem less like a direct weighing and more like careful bookkeeping. If a total sum is known, and some local contributions can be estimated, Then the remaining part can be assigned to the wider cosmic path. That remainder is the key. It represents the portion of the free electron column that most likely comes from the intergalactic medium and related diffuse structures beyond the immediate galactic environments. In this way, the hidden ordinary matter between galaxies is not measured by looking at it alone in isolation. It is measured by removing the better-known foreground and local terms from the total. The nearest contribution comes from the Milky Way itself. A burst arriving at Earth must pass through some portion of our galaxy, and the Milky Way contains ionized gas in its disk, spiral structure, and surrounding environment. That gas delays the signal before it even leaves the local galactic neighborhood. Astronomers therefore use models of the Milky Way's electron distribution to estimate how much of the dispersion measure belongs to our own galaxy. These models are built from pulsars and other radio sources whose distances and signal delays help map the ionized gas in the Milky Way. The models are not perfect, and uncertainties remain in some directions, yet they provide an essential first correction. Without subtracting the local galactic contribution, the intergalactic medium would appear more heavily populated than it truly is. Beyond the main body of the Milky Way lies a more extended region, often called the galactic halo, or circumgalactic medium. This region also contains ionized gas, thinner and more extended than the material in the galactic disk. A burst travelling toward Earth may cross this halo as well, and its electrons add to the delay. The halo is harder to model precisely than the Milky Way's denser inner structures, because it is more diffuse and less directly mapped. Even so, it cannot be ignored. The ordinary matter associated with our own galaxy extends beyond the visible stellar disk, and the burst records that local outer atmosphere before entering the truly wider cosmic path. At the far end of the route lies another local contribution, the host galaxy of the burst. Just as the signal must leave the Milky Way's material before reaching Earth, it must first escape the matter of its own distant galaxy. That host galaxy may contain ionized gas in its disk, halo, and local environment around the source. In some cases, the immediate neighborhood of the burst may be especially active, dense, or magnetized. Young compact remnants, star-forming regions, and disturbed local plasma can all add to the signal delay. These contributions matter because they belong to local astrophysical settings rather than to the vast intergalactic medium itself. Estimating the host contribution is more difficult than estimating the Milky Way contribution. The Milky Way surrounds the observer and has been studied in great detail. A distant host galaxy is observed from far away, sometimes only faintly, and its internal electron distribution is not known with equal precision. Astronomers therefore rely on localization, host identification, galaxy type, local burst environment, and statistical reasoning to estimate how much of the dispersion measure likely comes from the host. This part often carries larger uncertainty. A burst in a dense local environment may contribute more from the host side than a burst in a quieter and more diffuse region. The exact value cannot always be fixed with certainty, but it can often be bounded well enough to make the wider inference useful. Distance also helps. When a burst is localized to a host galaxy with a measured redshift, astronomers gain an estimate of how far the signal has traveled across expanding space. Redshift means that light and radio waves are stretched to longer wavelengths as the universe expands. The measured redshift of the host galaxy provides a cosmic distance indicator. Once that distance is known, the total dispersion can be compared with the path length. A burst that travels farther is expected, on average, to cross more intergalactic electrons. This allows astronomers to ask whether the leftover dispersion, after local contributions are subtracted, grows in the way expected for a universe filled with diffuse ionized ordinary matter. This layered subtraction does not produce a perfectly clean answer for every individual burst. Some lines of sight pass through denser environments than others. Some host galaxies contribute more. Some Milky Way directions are modelled better than others. Yet the power of the method grows with sample size. One burst can suggest. Many well-localized bursts can establish a pattern. If the remaining dispersion after local subtraction consistently matches what is expected from intergalactic plasma across known distances, then the case becomes strong. The hidden ordinary matter between galaxies is no longer merely plausible. It becomes the natural explanation for the measured trend. The method therefore depends on modesty as much as precision. Astronomers do not pretend that every electron along the path can be assigned to a region with perfect certainty. Instead, they estimate the known layers, quantify the uncertainties, and look for the residual contribution that persists across many events. The missing matter problem is solved not by one dramatic detection of a single glowing cloud, but by the careful removal of foregrounds until the intergalactic component stands out in the remainder. This is a quiet but decisive stage in the argument. The total dispersion measure shows that ionized matter lies along the line of sight. The subtraction of Milky Way, halo, and host contributions reveals how much of that signal must belong to deep space between galaxies. In other words, the cosmos is separated into local layers and distant layers, and the burst allows those layers to be counted in turn. The deep intergalactic share emerges not because it glows brightly on its own, but because the nearer contributions can be estimated and removed. So this section stays entirely with that separation process. The burst arrives carrying one total delay, but the route contains several electron-bearing regions. Astronomers model the Milky Way, account for its extended halo, estimate the host galaxy and source environment, and then examine what remains. In that remainder lies the intergalactic contribution, the part most relevant to the missing ordinary matter in deep space. The signal is therefore not just a measure of everything, it is a measure that can be peeled apart layer by layer until the wide cosmic medium begins to show itself with clarity. With the local layers estimated and removed as carefully as observations allow, a larger pattern begins to stand in clear view. The remaining dispersion in many well-localized fast radio bursts matches what is expected if ordinary matter fills the vast spaces between galaxies in diffuse ionized form. This is the central result toward which the earlier sections quietly move. The missing matter does not prove to be absent from the universe. It proves to be present in the plasma of deep space, distributed across intergalactic regions and galactic outskirts, rather than packed mainly into stars and bright structures. The strength of this conclusion does not come from a single spectacular burst. It comes from a growing sample. One localized FRB can show that a particular line of sight contains a certain amount of free electrons. Several localized FRBs can suggest a trend. Many localized FRBs, each with a measured host galaxy and a known redshift, allow astronomers to compare distance with dispersion in a statistically meaningful way. When that comparison is made, the relation follows the expectation that more distant bursts, on average, cross more intergalactic plasma and therefore carry larger cosmic electron columns. This is the observational foundation of the result. The hidden ordinary matter reveals itself not through one isolated event, but through repeated agreement across many paths through the universe. Earlier work already shows that FRB dispersion can recover the expected cosmic baryon content in broad terms. More recent studies with larger and better localized samples strengthen that picture by asking not only whether the ordinary matter is present, but where it is distributed. The emerging answer is calm and specific. Most ordinary matter appears to reside outside galaxies, mainly in the intergalactic medium, with a smaller but important share in the extended halos around galaxies, and only a minority inside galaxies themselves. In other words, the visible islands of stars are not the main storehouses of ordinary matter. The dim plasma between and around them is. This is exactly the kind of solution the missing matter problem has long pointed toward. The cosmic inventory derived from the early universe requires a certain amount of ordinary matter. Surveys of stars, cold gas, and other bright galactic components fall short of that amount. The natural suspicion is that the missing share occupies diffuse and faint environments. Fast radio bursts now test that suspicion directly. They show that a large fraction of ordinary matter is indeed spread through intergalactic plasma, so thin and extended that direct detection is difficult, yet not impossible to infer through signal delay. The result also brings order to what once feels like a scattered set of partial hints. Absorption studies, X-ray observations, Sunyaev-Zeldovich measurements, and theoretical simulations all suggest that substantial baryonic matter should inhabit diffuse warm-hot gas in the cosmic web and in galactic halos. FRBS do not replace these other approaches. Instead, they join them with a method especially sensitive to free electrons along long paths through space. That sensitivity is powerful because ionized hydrogen and helium dominate the hidden ordinary matter. The FRBs therefore measure the right component of the cosmic medium for the problem at hand. What emerges from the latest work is not merely that the missing matter exists somewhere. It is that the broad distribution of ordinary matter now appears consistent with the near-complete census. A substantial majority lies in the intergalactic medium. Another portion lies in circumgalactic halos surrounding galaxies. A smaller portion remains inside galaxies in stars, gas, and dust. The exact fractions can shift somewhat from one analysis to another because sample size, modelling choices, and definitions of environment vary. Even so, the larger conclusion remains steady. The long-missing ordinary matter is not missing in a fundamental sense. It is accounted for across diffuse structures of the universe. This does not mean every uncertainty has disappeared. Individual FRBs still carry host galaxy ambiguities. Some lines of sight pass through unusually dense or unusually empty regions. The Milky Way foreground and halo are not modelled with perfect precision in every direction. Host environments differ, and repeating and non-repeating sources may sample different local conditions. Observations indicate that these uncertainties remain real, and the growing field continues to refine them. Yet the uncertainties now sit inside a framework that already works. They influence the sharpness of the map, not the basic existence of the hidden matter. This is an important change in scientific posture. For many years, the missing ordinary matter problem is framed as a deficit between prediction and observation. The numbers suggest that something is there, but the direct evidence remains incomplete. With localized FRBs, the argument becomes much more direct. The bursts pass through the diffuse plasma, accumulate delay from its free electrons, and deliver that record to the telescope. Once local galactic contributions are removed, the remaining signal fits the expectation for intergalactic baryons. The problem shifts from whether the matter is there to how finely its distribution can be mapped. There's also a quiet elegance in the way the solution appears. The universe hides its ordinary matter by spreading it thinly through enormous volumes. The same geometry that makes the matter hard to image also makes it measurable by FRBs. A long path through a thin medium accumulates a detectable electron column. Distance, which usually weakens observation, becomes part of the method. The more of the cosmic web a burst crosses, the more of the hidden plasma it samples. The vastness that conceals the matter also provides the measuring track. For cosmology, this matters because it confirms that the standard large-scale matter inventory is broadly correct in its ordinary matter component. The missing baryons do not require a radical new category of substance. They require better tracing of ordinary ionized gas. That is a quieter resolution than many cosmic mysteries receive, yet it is no less profound. It shows that one of the long-standing accounting problems in astronomy can be resolved by reading the fine delay pattern of brief radio flashes from distant galaxies. So this section remains with the accounting itself. Across a growing sample of localized FRBs, the dispersion left after local subtraction shows that the expected ordinary matter exists largely in diffuse intergalactic plasma, with additional matter in galaxy halos and less inside galaxies than their brightness alone would suggest. The cosmic ledger closes not with a dramatic discovery of a new substance, but with the recovery of familiar matter in unfamiliar places. Deep space, once taken for emptiness, turns out to be one of the main homes of the ordinary atoms from which stars, planets, and life arise. At the innermost level of this story, the missing matter problem becomes a matter of tiny charged particles responding to a passing wave. The vast cosmic web, the space between galaxies, and the long route of a fast radio burst all reduce, in the end, to a simple physical encounter. A radio wave moves through ionized gas. Free electrons in that gas respond to the wave. Because of that response, the signal is delayed in a measurable way. What seems at first like an immense cosmological mystery therefore closes on a piece of fine physics that is quiet, ordinary, and exact. The most important particle here is the electron. An electron is a very light particle carrying negative electric charge. In an ordinary neutral atom, electrons are bound to a positively charged nucleus. Hydrogen, the most abundant element in the universe, has one proton in its nucleus and one electron around it. Helium has 2 protons and usually 2 neutrons in its nucleus, with 2 electrons around it when neutral. In the thin gas of deep space, however, atoms do not always remain complete. Heat, radiation, and collisions can strip electrons away from nuclei. When that happens, the gas becomes ionized. It enters the plasma state, where electrons and nuclei move separately. This change matters because a radio wave is an electromagnetic wave. It consists of oscillating electric and magnetic fields traveling through space. Bound electrons inside intact atoms can respond to electromagnetic fields in one way. Free electrons in plasma respond in another, since they are not tied strongly to a particular nucleus. They can shift more easily under the influence of the wave's electric field. That motion does not destroy the signal under ordinary intergalactic conditions. Instead, it changes how the wave passes through the medium. The plasma becomes slightly different from empty vacuum, and the radio pulse carries the mark of that difference. At this level, the hidden matter is not hidden because it is strange in composition. It is mostly the most ordinary material in the cosmos, hydrogen and helium, often with a trace of heavier elements mixed in. The difficulty comes from condition and distribution. The gas is thin, often hot, and ionized. It stretches across vast distances without becoming dense enough to glow strongly in simple ways. Yet ionization gives it free electrons, and those electrons make it visible to radio timing. A small particle becomes the key to a large census. The response of electrons to a radio wave is also collective. One electron contributes almost nothing on its own. The signal delay that astronomers measure does not come from a single encounter. It comes from countless electrons spread along a cosmic path, each responding slightly as the wave passes. The total effect is the sum of these tiny responses integrated across galaxies, halos, filaments, and intergalactic regions. This is why a flash lasting milliseconds can reveal matter across billions of light years. The signal gathers the combined influence of innumerable particles distributed through enormous space. That combination of the minute and the immense gives the result its special character. Cosmology often seems to concern only the larger scale's expansion, structure growth, galaxy distribution, and the inventory of matter in the universe. Here those large themes depend directly on small-scale electromagnetic physics. The cosmic web can be traced because ionized gas along its filaments contains electrons. The missing baryons can be counted because those electrons delay lower radio frequencies more than higher ones. A grand structure leaves its evidence through the behavior of elementary charges. There is also an important distinction between electrons and total matter. The Farabi method traces ionized ordinary matter specifically. It does not directly weigh stars, planets, or cold neutral gas in the same way, and it does not trace dark matter through electromagnetic interaction. What it reveals is the ionized baryonic component along the line of sight. That is exactly what makes it so well matched to the missing ordinary matter problem, because the hidden share is expected to live mainly in diffuse, ionized gas. The method is selective in a useful way. It is sensitive to the right physical component. Ionization itself links the microphysics to the large cosmic environment. In cooler and denser conditions, atoms more easily remain neutral. In hotter and thinner conditions, electrons are more easily separated from nuclei. The environments between and around galaxies often favor this ionized state because gas is heated by gravitational collapse, shocks, radiation, and energetic galactic outflows. So the large-scale evolution of the universe helps prepare the microscopic state that FRBs later probe. Cosmic structure formation determines where the gas goes and how hot it becomes. That thermal and dynamical history determines how many free electrons are present. Then the radio burst arrives and reads that state through dispersion. This means the missing matter solution is not only an observational result, it is also a physical fit between several layers of reality. The early universe predicts the total ordinary matter budget. Structure formation spreads much of that matter into diffuse cosmic environments. Heating and ionization create widespread free electrons. Radio bursts cross those regions and acquire frequency-dependent delay. Telescopes record the delay, and astronomers translate it into an electron column. Each step belongs to a different scale, yet the chain holds together. The logic runs from the earliest cosmic inventory to the smallest charged particles along a single line of sight. The role of hydrogen is especially quiet and central. Since hydrogen is the most abundant ordinary element, its ionized form supplies much of the free electron population in deep space. Helium adds more electrons depending on its ionization state, and heavier elements contribute less by total abundance. In that sense, the ordinary matter census depends largely on the simplest atom in the universe. The missing matter is not mainly hidden in rare substances or exotic chemistry. It is hidden in very common material spread too thinly to stand out. Radio waves are also well suited to this task because they can cross great distances through diffuse plasma without being extinguished. Visible light can be blocked by dust. X-rays require particular conditions for strong emission. Radio bursts, by contrast, can travel through much of the ionized medium while still carrying a clear record of dispersion. Their usefulness comes from balance. The plasma influences them enough to delay them, but not so much that it erases them. The signal survives, altered but readable. So the path from outer to inner comes to rest here, at the scale of the electron and the electromagnetic wave. The missing matter in deep space is found not by forcing the gas to become bright, but by allowing a brief radio pulse to cross it. The large-scale universe enters the data through tiny timing shifts produced by tiny charges. In that sense, the solution is both grand and modest. It concerns the matter budget of the cosmos, yet it depends on well-understood physical behavior, repeated countless times along a long path through plasma. The hidden ordinary matter of the universe is therefore not rescued by speculation. It is recovered by a chain of ordinary physics linking electrons, ionized gas, radio wave propagation, and cosmic structure. The deepest spaces between galaxies remain thin, dark, and visually quiet, but they're no longer mute. Through fast radio bursts, their free electrons leave a measurable trace. The cosmic web becomes legible through plasma, and the smallest charged particle helps complete one of astronomy's long unfinished counts. The long search for missing ordinary matter settles into a quieter picture than the phrase first suggests. Nothing dramatic vanishes from the universe. Nothing needs to be invented to fill the gap. The matter remains where the large cosmic inventory says it should remain, but it is spread through regions too thin and too faint to dominate the eye. It lies between galaxies, around galaxies, and along the broad structure of the cosmic web, mostly as ionized gas carrying free electrons through deep space. Fast radio bursts do not create that matter and do not disturb it in any lasting way. They simply cross it. A brief pulse leaves a distant galaxy, travels through plasma stretched across immense distances, and arrives with a small delay written into its different radio frequencies. That delay is enough. From it, astronomers read the presence of hidden electrons, then the wider presence of ordinary matter itself. A moment measured in milliseconds becomes a path measured across the universe. The result brings the outer and inner scales into calm agreement. The largest structures of the cosmos, the faint gas between galaxies, the ordinary hydrogen and helium of deep space, the free electron, and the travelling radio wave all belong to the same continuous physical story. The dark reaches between bright galaxies are no longer merely absence. They are part of the material body of the universe, holding much of the ordinary matter from which brighter things eventually form. So the cosmos becomes slightly less empty and slightly more complete. The visible lights remain islands, but the darkness around them is not hollow. It is filled with thin substance, shaped by gravity, heated by cosmic history, and revealed by passing radio flashes from far beyond the Milky Way. In that wide, quiet medium, the long-missing matter is found not as a surprise, but as a patient confirmation that the universe has been holding it there all along.